Mainly focus on chapter 10, since I did a review of chapter 9 already, and that's been recorded and posted. But this is a slide that kind of has all the big topics, okay? So I'm happy to share this slide with you guys in an email after this, okay? So you don't want to feel like you have to write every word down, all right? But let's look at these real quick. Chapter 9, you definitely need to know solubility. Like dissolves like, what solutes would be, soluble in certain solvents. It all has to do with intermolecular forces, things that are polar. It's the whole like dissolves like. Ionic and polar dissolve in polar solvents, non-polar and non-polar, okay? Increasing and decreasing solubility. So like if I wanted to increase the solubility of a solid in a liquid, you increase the temperature, okay? Salt, sugar, things like that are more soluble as you increase temp. Gases become more soluble as you decrease temperature, okay? And then Henry's law, which is concentration and pressure, solubility and pressure. The more you increase pressure, the more you increase solubility of a gas in a liquid. All right, that's Henry's law. Knowing how to calculate concentration using the mass volume percent, and then molarity equations. That was big stuff in chapter 9. Then knowing how to use molarity as a conversion factor in those 3-part problems, which it looks a whole lot like a titration problem, which you'll notice I have on chapter 10. If I give you the milliliters of something, you can convert it to liters, plug in the molarity, convert to moles, plug in a mole-to-mole ratio, solve for the volume of another solution you would need to react with or titrate that substance. Dilutions, electrolytes, and osmosis are also all have their own equations, right? So lots of equations there in chapter 9. And then chapter 10, the big topics were, if I give you an acid-base reaction or if I give you the reactants, can you identify which one is the acid and the base and then tell me what the products will be? Could you label conjugate acid-base pairs? Those are 2 big things. Acid-base strength. So knowing what that means, like I got a couple problems in a little bit. If you have a strong acid or a strong base, you know it completely disassociates. Much easier to calculate pH or POH or whatever, concentrations of H plus or OH minus if you have a strong acid or base, okay? But if you have a weak acid or a weak base, well, really just if you have a weak acid, how do you calculate pH in that sense? If I say you got a solution of a weak acid, what would be the pH we're gonna work upon like this? Anybody know what equation you use in that case? You can't just plug in the concentration that I give you into the negative log and say negative log of that equals pH, the way you could for a strong acid. What would you do in that case if you have a weak acid? There was an equation, because we said weak acids partially disassociate, which means there's going to be an equilibrium.
Isn't that one that's the pKa plus the log?
That's for buffers. Okay. That's for buffers. So you can't use the buffer equation for just a normal acid or base solution.
Is this the AHA equation or it's A on top and HA on top?
That's the buffer equation. So we are both talking about the same one. That's the buffer equation. We've said it 3 ways now. The one with the pK, the one with the log of A minus over HA, that's the Henderson-Hasselbalch equation, which is for buffers. So for weak acid, use Ka for weak acid, okay? Yeah. And you do the square, you end up doing the square root, okay? Because you plug in X and you have X squared equals. So anyways, we're gonna work upon like that. But that's if you have a weak acid. And then, so that was right here. And then KW, you got pure water. If I give you though, if I ever asking you what's the concentration of H plus or what's the concentration of OH minus, the easiest way to solve for that is with KW, okay? And it doesn't have to just be for pure water at that point, it's for any acid or base solution, but because pure water is present, we can use that, okay? And then buffers, the Henderson-Hasselbalch equation, we're gonna work upon like that. Titration, this really corresponds with molarity as a conversion factor. It's kind of the same thing there. And I did a problem like that last week on the review that's posted to Blackboard, okay, if you have questions on that. So again, I'm going to share these slides with you because there's a whole lot of really good problems on chapter 9. Henry's law, stuff that's brand new, stuff from the textbook, some stuff maybe I have worked, some stuff I haven't, some osmolarity problems. This one I worked on the review, so you can watch that or try to work it yourself, the Listerine problem. And then that's another one from the textbook on chapter 9 stuff. But here's where we get to chapter 10. So you're going to have this table, remember, on the exam. The way this will be most helpful to you is if I give you a problem and say, what's the pH or what's the whatever of this substance, you need to run over to this table and say, okay, is it strong or weak? Because then that's going to determine how you solve for pH. If you need to use Ka, You can just plug in the concentration into pH equals the negative log of whatever, or into KW or something like that, okay? All right, so here we go. What is the pH of a solution of 0.075 molar lithium hydroxide? All right, so hydroxide there is the base, right? Lithium is just the spectator ion. So let's go to the table and see, where do you see hydroxide? Is it a weak or strong substance? Lucas is just nodding at me, so I'm like, you just go ahead. Okay, it's strong. There we go. So we can just say that we have 0.075 molar of OH minus, okay? Because LiOH, because it's strong, will completely disassociate into lithium and hydroxide, okay? So now what should we do? We want the pH. All we know right now is the concentration of OH minus. There's two ways you can go about this. Anybody have an idea? How do we go? What would you do next? There's two ways you can go about this. We want the pH. I'll give you two hints. You can use KW, or you can use pH plus POH equals 14. What do you need to use KW since it doesn't give you the pH? Or the POH? Water's present in all aqueous solutions. This is definitely an aqueous solution. Yes, so you can definitely assume that you can use KW or the other equation here. So I guess I'll show it to you both ways. We got the concentration of OH minus, right? So we could plug that right in here into the equation for KW. What can we solve for at this point? We can solve for H plus because we know what KW is. What is the value of KW? 1 times 10 to the negative 14. So come right over here. We'll say 1 times 10 to the negative 14 equals the concentration of H plus. Why are we interested in the concentration of H plus? I thought we were trying to get pH. You need that to solve for pH. Times 0.075. Okay. So I'm going to cross divide both sides by 0.075. Cancels. And what is my concentration of H plus? I'll need y'all's help. -14. If you got it, shout it out. Divided by 0.075. I got 1.33 repeating times 10 to the negative 13. And that is my concentration of H plus. Now what do I do? One step away from getting pH. Yep, we know pH equals the negative log of the concentration of H plus, right? So I'll just take this right here that I just solved for and plug it in right there. So I'll do the negative log of that value. Olivia, you want to pull that door closed for me? I got 12.9 if you round. Anybody else get that? Okay. So my pH would be 12.9. All right, and that makes sense that this is a basic pH because we have a strong base here. The other way we could solve for this, is it going to confuse you if I show you two ways? No? Maybe you like that one better? Okay, so the other way you can solve for this, I'm kind of out of room here, but is we can use this equation right here. So how would we get, if we have the concentration of OH minus, that's what's kind of understood from the problem. How do we get POH from that? Remember what does P stand for? Negative log. So let's just take the negative log of 0.075. So let me erase these equations. So what I'm going to do is I'm going to say I'm going to take the negative log of 0.075, my concentration of OH minus, because that equals P of OH. And I get that P of OH is 1.12. Okay, now I know that pH plus POH equals 14. So I can subtract POH from both sides. And what happens is pH will equal 14 minus P of OH. Okay, so then we just come right over here and we say 14, well, pH equals 14 minus 1.12. Y'all like that way better? Different people like different ways. Yeah, that's why I show you all this equation, because I think it's a little easier. And you should find the same thing. Boom, pH equals, well, I got different decimals there, but right around 12.9. Okay. You know me, I'm not gonna count off points if you give me 1 or 2 decimals. Questions on that? The key here is that you recognize this is a strong base, which is why you're given this table right up here. That completely determines how you handle the problem. And I'm not going to give you a problem of a weak base. I might give you a problem for a weak acid where you're going to use Ka. All right. Very similar problem here. What's the pH of a solution? This is going to be a little bit easier though. Of 1.35 times 10 to the minus 4 HNO3. What is HNO3? Well, go to the table. Is this a strong or a weak substance? Anybody see it? And I won't give you anything that's not on this table for the sake of calculating pH like this. It's a strong acid. So what can we assume? Yep, complete associates into H plus and NO3 minus. And the concentrations of these things are the original concentration, 1.35 times 10 to the minus 4. And you see this problem is simpler because we're dealing with an acid and it says, what is the pH? So we actually already know the concentration of H plus right here. We just assume it's what the original concentration of the acid was because all of that acid will dissociate, every bit of it. So then we just say pH equals the negative log of our concentration, 1.35 times 10 to the minus 4. So why didn't I need Kw? Why didn't I need POH plus pH equation here? What's the difference? What's the difference in these two problems? Yeah, the first problem, we're starting with a base. So it's a little extra work if I'm trying to calculate pH from the concentration of a base. Okay, that's why Kw in the POH equation is helpful. Here we're starting with an acid. That's the difference. So we already know we directly know the concentration of H plus. Now we just plug it into our equation for pH. And it's not a buffer, so we don't need Henderson-Hasselbalch. Okay, it's not a weak acid. And that's why it's easier. Anybody got that negative log of that? Okay, so that's a few examples of just calculating pH. It's not a buffer. We're just using pH equals the negative log of H plus here. Notice we use that in both equations. We just had a little extra work on the first part because it was a strong base we're starting with. And we had to determine the concentration of H plus from the information we were given. Any questions on that?
How do I discern between these two?
The fact that you've got OH minus in that, and then the fact that this is a strong acid right here, I guess I could highlight it. That's a strong base. This is a strong acid. And I just looked at the table to figure out what's what. They both have hydrogen in them, right? So you got to go look at the table. Now I recognize hydroxide, OH minus. And I've been doing this long enough to know strong acid. But for you, just go look at the table. If you're dealing with a base, you're like, and I ask you what the pH is, you're going to have to either use Kw or the pH and POH equals 14 equation. But if you're dealing with an acid and it's a strong acid, you directly know the concentration of H plus, you just plug it into pH equals negative log of H plus. Okay. Oh, we've got our weak acid table. You see that? That's an indicator that we're dealing with a weak acid. So just calculate this is right from the book, by the way. Calculate the H3O plus, which remember that's synonymous with H plus, okay? For the 0.1 molar CH3COOH. Y'all might recognize this by now. That's acetic acid. Okay, you dealt with that in the lab when we did the vinegar titration. Okay, what is the percent of the weak acid? Oh, it says in the problem this, so I don't have that problem captured here, but it tells you that the pH equals like 2.88. Okay, that's the info from that previous problem that I think you need to do this one. But I honestly think we could do it without that info. It says calculate the H3O plus concentration for the 0.1 molar solution of acetic acid. What's the percent of the weak acid that dissociated? So I'm giving you a little hint here. First, determine the pH. Then we can determine what percent of the acid dissociated. So the info that we need is right here on this table where it says acetic acid. Whoops, right there. And we need this number. That is the, what is that? That's the K value. See, that's the K value. And remember, what is Ka? You got to be able to write this out. Any equilibrium expression is what? Concentration of what goes on top, what goes on bottom? Products over reactants. So what is good if this acid disassociates here? Let me move this down. Oops. If this acid disassociates, you got to be able to write this COOH. Remember, there's our acidic hydrogen because you recognize the carboxylic acid group. That was the one functional group we talked about. It's an organic acid. We're gonna have an equilibrium because it's a weak acid. So I'm gonna draw my double arrow. And if it disassociates, then we're just gonna have acetate, CH3, COO minus, and then we're just gonna have a hydrogen. It just breaks apart into its ions. Now we write Ka for this. Just move it back up a little bit. Which is products over reactants. So we got the concentration of acetate. And we got the concentration of H+, which to solve for pH, that is what we need, right? We need that. And then we have 0.1 molar of our acid. So I'm going to plug that in on bottom because that's my reactant, 0.1 molar. Okay, now remember, what do I do from here? Pretend that you don't know what pH is. We're going to solve for it and see if we get that. So we're trying to solve for pH.
So both of those are supposed to have the same concentration, right?
Yes, here's where you can assume that the concentration of this and this, our products, are going to be identical. If that dissociates, you can't make one without making the other, okay? So they're going to have identical concentration. So I'm plugging X for both of these things. And what else do I need to go ahead and do? Plug in Ka. I know what Ka is. So my equation becomes 1.8 times 10 to the minus 5 equals X squared over 0.1 molar. Did I lose anybody? Okay. Well, that's fair. It says click the join audio. Oh, no, I don't want to join. Okay, so how do we solve for X squared at this point? Well, not first. First, I need to move my denominator, right? Cross multiply by 0.1. And then it cancels. If it cancels, I'm just going to erase it. And then you take the square root. So square root of 0.1 times my Ka value, all under the square root. And what is H plus here, or H3O plus? Anybody got it? 1.3 times 10 to the negative third. I feel like we just dealt with that number. Oh, no.
Yeah.
Okay, 1.3 times 10 to the negative third molar. That is my concentration of H plus. Now we're going to take the negative log of that to get pH, right? pH equals the negative log of the concentration of H plus. So 1.3 times 10 to the negative third Negative log of that. My pH is, guess what we calculated? pH, double check me, 2.89 if you round. Okay, so that's what that initial problem gave us in 10.53. And we just double check that. So, whoops. Now, the question saying though, the question in this problem says, what percent of the weak acid disassociated? How would we do that? How do you solve for percent? If I ate 2 pieces, if there were 8 pieces of pie and I ate 2 pieces, what percent of the pie did I eat? Yeah, I ate 2 pieces of it. Then I ate 25. So how did you just solve for that in your head? We're gonna do the same thing here. What did you do? 2 divided by 8 times 100. So you did the part that I ate divided by the whole pie. And you said times 100. It's the same idea here. The part of the acid that dissociated divided by the whole concentration of the acid times 100. The part that disassociated is this part right here. Okay. Oh, you can't see that. That's the part that disassociated, what I highlighted, which you now cannot see at all. Okay. And then the whole concentration of the acid was what the problem gave us, the 0.1 up there, right? That's my whole concentration of the acid. So I'll do part divided by whole times 100. So what we'll do is we'll say 1.3 times 10 to the minus 3 divided by 0.1. We'll say times 100. We'll figure out how much of this acid, what percentage of it is associated. Did you get 1.3%? Or did I do that wrong? Is that what you got? Yeah, it should be 1.3% of the acid. It's a pretty weak acid. Not very much of it disassociates. Okay. So that's a weak acid problem using Ka. All right. This one talks about buffers, but let's see what it's asking for. Which of the following buffer systems? And this is again right out of the textbook here. Would you use if you wanted to prepare a solution having a pH of approximately 9.5? So if you remember on the video where I talk about buffers, that was the longest one because I walked you through a whole problem, which we'll do in a minute. This is not a buffer problem yet, where we need to use Henderson-Housebuffer. There was a part of that where I said, if you want a buffer, well, I talked about qualities of a good buffer. Where was that? Yeah. So the one that has a star by it, this means that an HA to A concentration or ratio works best as a buffer when the solution is being kept at a pH that is the same as its pKa. And I showed you mathematically why that is. Okay, the log of 1 over 1 or whatever over what same concentration is 0, and that part of that term of the equation falls out, and then you have pH equals pKa. Okay, and that's when you have the buffer at its strongest. Okay. And so we're given the pH in this problem. We need to find the pKa and see which one has a pKa closest to the pH that we're told. That's all we got to do here. So we're told that we want the pH to be 9.5. And by the way, looking at these components here, which component, so here's the slash. So it's either this component or this component. Which one is the weak acid? That's what you got to decide, because we're about to go get its Ka value. Do you think it's H2PO4 minus or HPO4 minus 2? Whatever has the what? It's not whatever has the most negative. It's going to be whichever one has the most hydrogens. Okay. This one is going to be the weak acid. This is going to be the conjugate base. You see why? Let's look at this. H2PO4 minus. So HPO4 minus 2, this right here, is this substance once it's donated a hydrogen. So let's draw the dissociation reaction. H plus HPO4 minus. You see how when this is acting as the acid, it's a weak acid. But when that's acting as the acid, this becomes the conjugate base. If this is the acid, what's the conjugate base? Oh, that should be a -2. Yeah, so if this was my weak acid, then my conjugate base would be this, but that's not what we have. We have, you know, the two substances I've circled up here. So the one with more hydrogens got to be the weak acid. That's the one that disassociates and gives away hydrogens, which is what acids do. They're proton donors, remember? All right, so now that we know what the weak acid is, so for substance A up here, how do we determine if it would give us a buffer system with a pH around 9.5? What do we need to go do? You will have this table right here on the exam. We want the pH kept the same as its pK. Do we have pK? Remember I worked through, when I talked about these, I then worked through this problem right here. I give you a bunch of different weak acids and I say which one would be best if you're trying to keep one at a buffer system at a pH of 5. All we did is we walked through and we calculated the pKa of everything. I said, okay, which one's close to the pH? Same idea as what we're going to do here. You just had to identify what the weak acid was. So let's go get the negative log of it's H2PO4, right? Which is right here. So that's the Ka. We want to calculate the pK. And how do I do that again? What does P stand for? Negative log. So just take the negative log of Ka, right? Which is 6.2 times 10 to the -8. So we'll just do pK here equals negative log of 6.2 times 10 to the -8. That's the K value. And what do we get? Okay, so the pK equals 7.2. Is that close to 9.5? Not super. Let's see if we can get closer. So B we'll do down here. Now I want you to look at B. We got NH4 plus and NH3. Which one do you think is the weak acid and which is the conjugate base? That's right, Will. So let's go get the Ka value for NH4 plus. Anybody confused on how he knew NH4 plus was the weak acid? The one with the more hydrogens, right? When that disassociates and gives a hydrogen up, you're left with NH3, which is the conjugate base. And here it is right here, 5.6 times 10 to the -10. So we'll do the same thing, find the pKa. So pKa this time is the negative log. What do we say, 5.6 times 10 to the minus, I forgot, 10 to the -10. And what is the pKa here? Way closer. So I would want to use B, a buffer system like that. So all I did is I identified what, I didn't even use the concentrations. I didn't have to plug anything into the Henderson-Hasselbalch equation. I just calculated the pKa of the weak acid and said which one's closest to 9.5 there. That's all that question was asking for. But since a buffer problem is going to be on the exam, I went ahead and wrote a buffer problem for, so since B was our answer, this is what we're going to assume our buffer is, right? The ammonia buffer. And we just calculated what the pH would, well, we calculated what the pKa would be. But I want you to, this is a buffer problem. So a buffer problem will have 3 parts. I've got parts 2 and 3 right here. Part 1 would just say, tell me what the pH is, okay? We want the pH to be close to 9.5, but we can calculate what the actual pH will be now that we have the pKa. This is where you use the Henderson-Hasselbalch equation. So part 1 of every buffer problem will say, what's the pH? So we want to find what the pH is. We're going to assume that B here, the ammonia, and it gives you the concentrations, is our buffer. So what is the Henderson-Hasselbalch equation? I kindly decided to give you Ka and Henderson-Hasselbalch on the resources page. Okay, so those two equations will be on there, but I didn't put the equations for chapter 9 on there. So here, pH in the Henderson-Hasselbalch equation is equal to pKa plus the log of the conjugate base over the weak acid, right? So we're going to plug all that in. I need to shrink this down. So I'm running out of space. So pH, this is part 1 of a buffer problem. I guess I could draw a line. Equals 9.25 plus the log. Which one's my conjugate base again? Yep, so we'll plug in the 0.12 over the 0.08. Oh, 0.8. I just wrote 0.8. And we'll solve. So this is the Henderson-Hasselbalch equation we're using. Why? Because it's a buffer. So we can't just use pH equals negative log here. We have to use Henderson-Hasselbalch because we have 2 components to our buffer. Okay, I got 9.43. Anybody else? For my pH? I'm out of room. Okay, pH equals 9.43. So that's part 1. Now, parts 2 and 3. So this will be part 2. This will be part 3. Say, what happens? How does my buffer respond when you add strong acid or strong base? And it doesn't matter what order we do these problems in, okay? And how are we gonna go about doing this? So in part 2, it says, what if I add, I probably need to shrink that down a bit because that's like almost everything. I'm gonna say, we're gonna add 0.03 moles. So I don't wanna wreck my buffer. Say we'll do 0.045 moles here. Okay, so it says determine the pH if you add 0.03 moles of HBr to 800 milliliters of the buffer system in the previous problem slide. And since B was the one we wanted to go with, that would have the closest pKa. That's the one we're not going to assume that we're working with. Although you could do this with part A too. All right, what do we need to do? Right, so HBr, is this an acid or a base? This is a strong acid. First thing we need to do, step 1, is find the molarity. So we want the molarity of HBr. And I do that by calculating what? What is molarity? Molarity is moles over liters. And I got the moles, it's 0.03 moles. And I have milliliters, so just divide by 1,000 there. And that should be divided by 0, you'll divide by 0.8 liters. So that's going to be 0.0375 molar. All right, now what do I do? Remember, how does a buffer work? If I'm adding acid, how is it going to neutralize this acid? Remember the little buffer diagram? I'm not going to have you draw it out on the exam or anything, but I just think it's helpful here. So our buffer system looks like this. An H4, and then on the other side, we got our conjugate base. We're adding strong acid, and that's going to disassociate into H plus and Br minus, okay? This right here is threatening the pH of our buffer. The whole reason we have a buffer in our solution is because we don't want pH to change. or our biological system or our laboratory experiment or whatever it is. So one of these components is going to have to react to neutralize this acid. Which component is going to do that? Do acids neutralize acids or do bases neutralize acids? Everybody knows the answer to that. Bases. So which component is our base here? So this is going to swoop down, pick that up, and what's it going to make? NH4+. All right? That's how it's going to work here. So we need to set up a ice chart to see how the concentrations of these things are going to change once all of this HBr is neutralized. We get those new concentrations, we plug them into Henderson-Hasselbalch, we calculate pH. That's what the ice chart is for. So step 2 is set up your ice chart. So we got NH4+ and we got NH3. So our initial concentrations are what? 0.08 molar, and was it 0.12 molar? And I got that where? From the previous problem. That is the part that we'll plug in every time into the Henderson-Hasselbalch equations, or into the ice chart. Sorry, not the Henderson-Hasselbalch. You plug it in the Henderson-Hasselbalch equation for part 1, but you have to recalculate new concentrations for parts 2 and 3. Okay, now it's going to change by how much, these concentrations in my ice chart? This molarity, yep, that we just calculated. Now remember the phrase I have here, because everybody's confused on which column do I add it to, which one do I subtract it? When you add acid, HBr is acid, which is why I wrote this out. When you add acid, you add to the weak acid column. Subtract from the other column. So add 0.0375, and we're going to subtract, from this side. Okay, then we recalculate. So 0.08 plus 0.0375 is 0.175. No, 1075? 1125. Oh, 1125. Is that what you said, Lucas?
Oh, yeah, 75, sorry.
So I was like, that's right, it's 11 and then 75. There we go. Okay, and then the 0.12 minus, what'd y'all get? It's like 0.8 something. There we go. So our concentrations have now changed. These are the new equilibrium concentrations of our buffer components. This is what we plug into Henderson-Hasselbalch equation. Okay, so we're going to go right up here. Henderson-Hasselbalch is pH equals the pKa, which we already calculated the pKa. It was 9.25. Remember, we use that right up here. 9.25, same pKa, that doesn't change. You don't plug in Ka, you plug in pKa. So 9.25 plus the log of, it's remember conjugate base over weak acid, 0.0825 over 0.1175. So what is my new pH? Anybody got it? We got 9.0, well, let's just round, 9.1. Okay. And then the last part of the buffer problem here says determine pH if you add 0.045 moles of, now we're adding strong base to 950 milliliters of the buffer system in the previous problem. So same buffer components here. First step is you calculate the molarity of the strong base you're adding. So the molarity of NaOH here is going to be the moles, 0.045 divided by the liters, 0.95 liters. Okay, so my molarity will be 0.0474. Okay, step 2, set up the ice chart. Plug in your initial concentrations, same from the previous part. I don't know if y'all can see this. I probably should zoom in, shouldn't I? And then the molarity that we just calculated, that's what's going to change these concentrations by that amount. Remember, we're adding base here, so we add to the base column. Because the weak acid is going to sacrifice itself to neutralize this NaOH. Oops. Units, units, units. Then you calculate your new equilibrium concentrations, 0.08 minus 0.0474. So I got 0.0326. That's my new concentration of my weak acid. And 0.12 plus 0.0474. I got 0.1674. Now I got my new equilibrium concentrations. This is what I last step here. Plug into the Henderson-Hasselbalch equation, which says that pH equals pKa, same pKa as above, 9.25. Plus the log, it's conjugate base over weak acid. So 0.1674 over 0.0326. And we can see the buffer does a good job of keeping pH right around 9.5. And a strong base, a strong acid are added. Whew, that's a lot of work. Okay. So each problem will be worth, part 1 is the easiest, but parts 2 and 3 will be worth a good amount of points each. We've been going for about 45 minutes, and so this is the last problem I had. And then we probably got to wrap up. I think people are coming in here at 11. So, oh, it says problem 95 on the homework, which, by the way, that's due by the end of the day. And the quizzes and stuff, if you haven't taken the quiz yet, or the attendance quiz, due by noon today. So how many milliliters of 0.324 molar of H2SO4 would be needed to neutralize 60 milliliters of 0.175 molar KOH? This is a 3-part problem. This involves just content from chapter 9, using molarity as a conversion factor. Or you could think of this like a titration problem. We got acid in our flask, and we ended up using 60 milliliters of KOH to neutralize that. Okay, you work those problems the same way. So where do I start here? What I'm thinking about right now is this slide. Oh, it was down the other way. Right here. I'm thinking about this slide because this is going to tell me exactly how to go about this. So we've got some sort of acid, H2SO4, and some sort of base, KOH, and it's going to make water, and it's going to make K2SO4. Okay, we got to balance it, so we'll need a 2 there, and I think, is that it? Maybe a 2 in front of water. okay? And we're given that we have 60 ml KOH and what the concentration of that is. This says start with volume of solution A, and I happen to write the acid first, but don't, I guess that's misleading here. We're not going to start with the volume of the acid because we don't have the molarity of the acid yet. We have the molarity of the base. So we're going to have to start with the volume of the base and immediately use the molarity to convert to moles. We can't start with the volume of the acid because we don't have the molarity of the acid to convert. That's actually what we're, oh wait, we don't have a volume of the acid, we're given the molarity. I didn't read the whole problem. Okay, but anyways, we're gonna start with the only volume we're given, okay? So 60 mLs, and the first thing we're gonna do is convert to liters. So 1,000 milliliters for every 1 liter gives us 0.06 liters, right? Now, what is that? You know what I can do, I realized? Now I can view these. I don't know if you can even see both really very well now. But the first thing I do now that I have the volume in liters, I want to use the molarity to convert to moles. The molarity of KOH is right there. It's the 0.175 molar. Okay, and you can rewrite that as 0.175 moles of KOH per 1 liter. That is the molarity. Right? So I'm going to use that. I'm going to convert liters to moles. So for every 1 liter, it was 0.175 moles. And this is the KOH we're talking about. So you notice liters cancel. And now we've done step 1. Step 2 says use the coefficients in the balance equation to find the mole ratio and plug in the mole ratio to convert from moles of KOH to moles of H2SO4. Okay? And I actually wrote that right up here. Again, I don't know if you can see this very well, but it's a 1 to 2 mole ratio. Okay. So I'm just looking at my coefficient here and my coefficient there. It's an understood 1. So it's a 1 to 2 mole ratio. So I have moles of KOH on top. And I want to cancel moles of KOH. So I'm going to say for every 2 moles of KOH, it's 1 mole of H2SO4. There is my molar ratio. That is step 2. And notice that moles of KOH cancel. And I'm trying to find how many milliliters of this acid. So I'm well on my way. Let's see what our diagram tells us the next step is. Once we did step 2, use the coefficients in the balance reaction, we're at moles of H2SO4 now. Now, the last step is use the molarity of our H2SO4 as a conversion factor to go from moles to volume. And I'm given the molarity right here. Okay, so I think we can shove that out of the way. I think we can just focus on this now. So my last step, I'm going to plug in that molarity, which is I want moles to cancel. So I'll put the 0.324 mole part on bottom. That's per 1 liter. Moles of H2SO4 cancel. And so what I'll end up, oh boy, I'll start here. Since I already got my answer for liters, I got 0.06 liters times the 0.175 divided by 2 divided by the 0.3. It looks like I crossed out. I don't want to cross out 0.324, just the moles. Divide by 0.324. What do we get for the volume? It'll be in liters right now, and we can convert to milliliters at the end. 0.06 times 0.175 divided by 2 divided by 0.324. Anybody? .0162, and then you just convert this to milliliters, right? Times 1,000. For every 1 liter, it's 1,000 milliliters. So that would be 16.2 milliliters. Your answer there. So this is, okay. This is very similar to our titration problem. Not quite the same, but this is using molarity as a conversion factor. And this was an acid-base reaction. So I think that's about all we